there's definitely opportunities that are available. We do have a membership. You can join. I think it's $40 for individuals and $500 for corporate membership per year. $45 per year. I'm sorry, for individuals, $500 per year for your corporation. If you'd like to be a member, get a hold of Guy. He's right there. Cool gray shirt, gray glasses. Yep, that's Guy. Let's see, what else do we have here today? Again, thanks PayPal. If you need Wi-Fi, it's PayPal guest, and safe payments is your password. Right. We have today. Sorry. Bathrooms. Bathrooms are out the door to the right and then to the left. So out the door, turn right, turn left, and yeah, vending machine as well. So. Members, and we usually ask people who are looking for work. So is anybody looking for work at present? What do you do?
I'm a software automation.
Okay. And does anyone have work that they are trying to fill positions for? No? Whatever. Just made a connection. Beautiful. All right. No, thank you. Again, the cell phone thing, it was a joke, but honestly, if you can silence them, I know lots of people are on call. I am as well, but make sure you put it on vibrate, silent, whatever. Set phasers to stun, right? Stole that joke. See? Anyway, today Sean Suchter is here. He is the founder and CTO of Pepper Data, and today's talk is on building big data on top of Kubernetes. So I'm going to drop the mic now.
Very good.
There we go.
Thanks, Glenn.
Thank you. Thank you.
Yeah. Thank you. And yes, indeed, that's the talk I have prepared. So that's good. So I'm going to be talking about a whole bunch of stuff here. So I apologize a little bit if I seem like I'm going a little quick, because there's just a lot going on here, and I'm going to try to cover a lot, as much as possible. So things I'm going to do, I'm going to talk a little bit about just very brief introduction to Pepper Data and what we do and why we're interested in this. I'm going to give an intro to Kubernetes, and then why you might want to do big data on Kubernetes. So what was the genesis of this entire effort? And then talk something about the design of some of the various components that are involved in this. So then some deep dives into Spark and HDFS and some of the problems and how they actually work. And then I've got a very brief demo of the thing actually running, and then I'm going to talk about the future stuff that's going on. So basically our company, Pepper Data, we're about 5.5 years old. We're really all studying performance and big data and how developers and operators use it. What happened here? So I'm one of the two co-founders. Chad is the other co-founder. I used to work on web search for a long time, so I used to run Yahoo search when it was still their thing. And then I went to Bing, and we started up a search office in Silicon Valley. And I was for a while the only place that had a combination of all of Facebook and all of Twitter and all of the web, and so that was kind of fun. And sometimes one of the interesting things that happened at Yahoo was we were the first deployment of Hadoop. This is when we were happy if it stayed up on 10 nodes for a day. It's better now. My co-founder Chad is the first one to ever make money with Hadoop. I was just a cost center. He made billions of dollars for Yahoo, so that was good. Ash Munshi is our CEO. He's done a bunch of different things and knows a lot about big data and machine learning. We're around 20 or so people. All of our products are basically about developers and operators of big data systems. So we have things that help along this whole the entire spectrum of the DevOps cycle. From what happens when you're actually operating things to what happens while you're developing things. If you want to learn more about those, ask me or go see our website. But this led us to we have a lot of customers that are at very large scale. Right, and the defining attribute of our customers really is they're in production, right? And they really care about how their big data systems are operating, and they care about their applications, and they care about whether they perform well and whether they work reliably, and what's wrong when they break, because some of them are on pager when these things go off, and there's actually money attached to these things. And so we've definitely seen this trend over the last few years that big data has moved from purely experimentation into actual production, right? And so these things are not just toys and not just science experiments, but actually matter to the business. And it has tended to mean that the operationalizing of big data has been a real DevOps play. So it's very common that the people who wrote the big data applications are also the ones who are getting paged when they don't work right and deploying new versions of them. Sometimes they're also the ones operating the clusters, right? So and this means that the big data systems themselves are requiring more stability. And these things that used to be just ad hoc data science efforts, where there was really just one person maverick doing things, you had to have lots more collaboration and communication. However, there's one thing that really hasn't been solved very well, which is this divide between big data systems and the rest of IT, right? I kind of sometimes say that there's this big island, right? There's this continent, which is IT, which does everything. It has your serving and your mail systems and everything else your IT organization does. And then there's this island off the side, which is the big data systems. And never the twain shall meet, right? They tend to be separate people, separate systems, separate hardware, sometimes separate data centers, separate processes, separate business units, separate groups, everything's separate. And that kind of sucks. Because you shouldn't have to do parallel things. And this really impedes business progress because it means you want to do anything with big data, you can't because I got to go to those guys, right? And that we'd like that to be better. So Kubernetes is actually a way to help with that, and I'll kind of explain why. So first I just have to say, what is Kubernetes? Now, I definitely need to decide how much I need to explain this. I do need to understand how much the audience knows. So I'm going to start with an easy one, and literally everyone should raise their hand because my question is, who has heard of Kubernetes? Okay, good. Everyone has heard of it. Okay. Keep your hands up for a second. You'll get to put it down. Who thinks they know what Kubernetes does? Okay, that's pretty good. That's pretty good. Okay, who has ever used Kubernetes? Okay, a few hands went down. Who ran kubectl today? Okay, so we got a few. Okay, good. So that gives me a good sense. All right, so I can go quickly through part of this, but not other parts. So Kubernetes it's an open source system that allows automation, scaling, deployment, management, right, of containerized applications, right? And so it is it's an automation system that is specifically designed from the ground up to be about containerized applications. So it's very opinionated about that. It is definitely it's an open source thing with the whole ecosystem now. It's definitely born conceptually from the Google Borg system. Lots of people have heard that. But it means it's got the basic paradigm of how Kubernetes works is a very sound paradigm. So why do we have, I'm going to go a little more into what it means by containerized, but mainly one of the things you want to do if you have an automation system that is running many things, you've got a pile of hardware and you've got a pile of applications, you want to throw those applications at the hardware, you need isolation, right? It used to be the case that we isolated by putting one application on one piece of hardware, and since most of the time the application didn't just reach out to the box next to it, it's fairly well isolated. But now that's kind of inefficient, and it's also really hard to deploy rapidly a lot of apps that way because you don't want to keep provisioning hardware. So Kubernetes provides a model for isolation. Each container gets its own file system. It's extremely lightweight. And there's lots of ways to express different semantics you want of different file systems and different mount points. And it also, and this is super important, gives you a particular networking paradigm that you can use. And it gives, each container gets a specific IP address, or sometimes usually just one, and it manages ingress and egress and lots of things like that. And you can use whatever ports you want. Right? And that's super important too, is that you can use whatever ports you want. So that means you don't have to change your application a lot. Kubernetes, and this is a thing that is dated now, but you can kind of see the trajectory. Kubernetes has become extremely popular. If you look at the things that you might consider its competitors, things like OpenStack, Mesos, Docker Swarm, these things, as of the blue line, for anybody who's having trouble reading the legend, the blue line is definitely, as of 1 year ago, roughly, was already on the upward trajectory. And if this trend has continued, so it's clearly the most popular thing, the hottest thing in this space. And there's, in my opinion, good reason for that. Explaining all of the reasons why I'm such a big fan is beyond the scope of this talk, so I'm not going to get into all of that. But I am going to define a little bit, because it'll be important to understand how big data integrates, what the containerized model of Kubernetes is. So basically, each thing in, basically a container, right? And in one of the most common container technologies nowadays is Dockers. Everybody's heard of this. What do containers basically give you? You can have very repeatable builds and workflows, right? Because you know exactly what's going into your containers, and then when you run things in your containers, they have exactly the same file system state when they start up, and they have exactly the same OS image, and they have very well-defined semantics of the environment of the things you're going to run. So that's nice. Right? It means and because you've got a very strict definition, it means they're very portable. Right? It's very easy to have extremely precise control. This ends up meaning that your development cycle and your deployment cycle, and especially if your deployment cycle is part of your development cycle, can be very rapid, right? Because you can, these are much lighter weight to build than, say, an entire OS image, right? And so you can just focus on your software and you can iterate very, very quickly. I'm talking, the automated build parts of this can be seconds, right? So they don't really have to interrupt very much your train of thought. And it ends up meaning that because you can share things on hardware very efficiently, and they're so lightweight, you can get things like better infrastructure utilization, both because you can pack more things onto a node, but also because you can deploy things really fast, right? So you don't have a lot of downtime. So now, going a little more into Kubernetes, what do we see here? So basically Kubernetes, the system is you've got a bunch of users, right? There's an API that they use. There's command line interfaces. There's also a GUI that I think got washed out or not labeled correctly. But then there's a master system, right, that has a bunch of services, right? The API server and the scheduler that gets containers onto various nodes, various controllers, and then on the nodes, the hardware, the VMs that you're using to run your containers, you've got these things called kubelets, which are actually launching and managing and keeping your containers up. And when something dies, it tells the master, and maybe the master decides to start it again somewhere else, right? And so this is what the management is doing for you. So a key concept that I've got to explain what the terminology is in Kubernetes are nodes and pods. So a node, right, let's say you're deploying this on bare metal. A node is one of your bare metal boxes. If you're deploying this in Amazon or Google Cloud, right? A node is one of the VMs that they give you. And then a pod, right, is a set of co-located containers. So all of the containers in a given pod are guaranteed to be on the same node. And this is super important, you declaratively say to the master, this is my definition of what should be in this pod. Right? And it's important that it be declarative, not imperative. You're not saying, go create go create something now and then put this on it and then put this on it. You're actually saying this is completely the definition of what I want to have, and that means the master can do things like restart them for you because you told it everything it needed to know. The pods all have their own IP addresses, which is why they can use whatever ports they need. And volumes, right, disk storage, can either be local, which you might do for some cases persistency reasons, many cases for performance reasons, or you can have network attached volumes. Kubernetes is not very opinionated about what kind of storage you use. It wants to allow you multiple options. It is opinionated about the containerness and the semantics of the network that it offers, even though it has a very pluggable networking system. So now I'm going to talk a little bit about why you might want to have big data on Kubernetes. And a big reason is that gap that I was talking about earlier, where you have the island and then you have the mainland, right? Because Kubernetes was not invented as a system to do big data, right? This came much later. Kubernetes is invented as a system for the mainland. It's for running services. It's for, and they might, frequently they're microservices because that works really well with containers, or they might be big monolithic things too, right? But it's about services, they might be long running, but it was definitely not invented to do big data, right? So that, but it turns out that it was very easy and very feasible to run big data things, and obviously I'm going to talk about that, on Kubernetes. So this means that you can very effectively, take that island and that mainland, and you can start merging them. And this is the first time this has really been feasible for the last, dozen or so years. So you get to resource share, right? And that's good from a hardware efficiency, but it's also super important from a human efficiency, from an operator efficiency, from a developer efficiency, because you don't have to use completely separate systems. And Kubernetes in particular is particularly nice because of that, that up and to the right chart that I showed earlier. Kubernetes has a really nice ecosystem surrounding it. There's lots of add-ons across many different things, and the ecosystem is just growing. And obviously, big data on Kubernetes is one instance of that. So let me define what big data on Kubernetes really is. So there's a set of projects, and this keeps growing, right? If I was to give this talk, many months ago, I would have had to leave off Airflow. The core thing of big data and Kubernetes, we really started from what would a modern big data stack look like. We started from Spark, right? Spark is an engine that allows all kinds of different computations. It can do batch, it can do SQL, it can do interactive, it can do streaming. So that's very, and it's poised to be the de facto future of doing many different big data computations. So said, hey, if you're going to build a modern stack, might as well just start there. In many cases, and I'm going to talk about why you still need a storage system, so particularly the HDFS subsystem out of Hadoop is part of this. TensorFlow works natively well on Kubernetes. I'm not going to go a lot of detail into TensorFlow, mainly because I don't know as much about that as I know the other systems. And Airflow is a workflow scheduling system that allows you to execute arbitrary DAGs of complex workflows, and that also is working very well natively on Kubernetes. So I'm going to overview a few of these. So first, Spark on Kubernetes. So one question is, what do we have to do to Spark to make it speak Kubernetes? So Spark has basically a core system, and it has a bunch of applications that you can do on top of it. Spark SQL if you want to do SQL. There's a machine learning library. You can do streaming computations. There's a graph processing thing, and there's a few more higher level things you can do on top of this Spark core. And for many years, the only infrastructures that Spark could run on, Spark originally ran standalone, and it ran on Mesos as a possible backend, and then Yarn, of course, being so prevalent in the big data universe, Spark got Yarn support, and that's basically you're looking back 5-6 years now, and these three were the name of the game for the entire last half decade, right? It was all about these three things, and we had to add one more, Kubernetes. So the backend where Spark can get its work done used to be just these three things, and we had to add one more. So this was definitely a invasive change inside the Spark core. Next question is, what did we have to do? A little more about what it meant to teach Spark to do Kubernetes. So inside the main Spark program, which is called the driver or sometimes Spark submit, there is the core engine, and the core engine always has a what's called in Spark a coarse grain scheduler backend, right? It had one for Yarn, it has one for Mesos, and it has a very trivial one for standalone. We had to add a new scheduler backend, which was the Kubernetes scheduler backend. And the abstraction here is not always as great as one might want, so there was many things that had to change inside of Spark to add this new coarse grain scheduler backend. It had to handle things like resource requests, authorization, and several other places where it had to communicate with Kubernetes. The next question is, what did we have to do to Kubernetes to allow it to speak Spark, right? And the answer was, we didn't have to do anything to the Kubernetes core. So Kubernetes was already flexible enough to do all the things that we needed to do with performance and a nice API. However, we did add a few additional services that Kubernetes allowed us to run, right? But they're all just additional applications as far as Kubernetes is concerned. We didn't have to make core modifications. We had to add a staging server, and I'm going to explain a little more what that is and why. We also had to have a shuffle service. When Spark runs its computations, it has to hand data between different parts of itself, and that's called shuffling. So there had to be a service. There's a reason why you need that to be a separate service. I'll talk about that. And there's also a extensibility API in Kubernetes that allows us to add descriptions of what Spark means. It's called third-party resources, or it used to be called that. Now it's called custom resource descriptions, and that allows us to make Spark seem like it's built into the Kubernetes core, even though it's actually a completely separate application, right? Because you can use this extension thing. So the custom resources allows us to have this additional endpoint, and the shuffle service and the file staging server are just pods that are running inside of Kubernetes. So one important thing about running Spark applications typically have dependencies. And when a dependency here, a few examples, right? Your code that you want to run that is doing whatever analysis you're asking Spark to do, you wrote some code. That's a dependency, right? So a lot of the time you have to get your code into the actual, all the workers that Spark spawns inside of Kubernetes. You might have some file that you need to load up as a hash table that every single little worker is going to load up in RAM. That's another kind of dependency, like a dictionary of words is a common one. So there has to be a way to get those dependencies into all of the Spark worker containers, right? All jars of code or dictionaries or things like that. In Yarn, this is typically handled by HDFS, because you had this well-known file system, and you could just say, well, it's right there on the file system. Everybody can just retrieve it. But in Spark, on Kubernetes, you don't necessarily have always the same file system, so we can't depend on that. So there's a few ways that you could get these dependencies in. One is, of course, you're using Dockers. Well, you could put the dependency in the Docker. And sometimes if you're running the same job over and over, or it's the same dependency that's used for many things, that's a pretty good answer. Sometimes you could, you want to get those dependencies from some external file system. Like you could get it from an HDFS, or you could get it from an HTTP server, you could get it from S3 or Google storage. Or you could also use this file staging server, right? So there's this pod, this additional application that runs in pods that was created as part of this project, which basically runs in the Kubernetes, and you're allowed to hand it files, and then your worker pods can go and pull those files back out, right? Because you can't necessarily depend on either of the other methodologies. There's also a bunch of very convenient administration things that we kind of get for free because we're using Kubernetes here. You get separation of users via namespaces, you get quotas, you get various auditability, lots of things that you kind of get. So now I'm going to do an overview of HDFS. So first question you got to answer is why? Why would you, when would you be using HDFS? So of course, Spark on Kubernetes supports using cloud storages like S3 or GCS, right? So if you're running in a cloud, you might just be pulling your big data out of their storage system. However, that's not always where you want to store your data, right? And so sometimes you need, you end up wanting, your data is already stored in HDFS, right? Because you have an HDFS somewhere else. Maybe you're not in the cloud, right? Why do you end up frequently, or even in the cloud, you might have an HDFS there. Why might you have this? There's a few reasons. One, sometimes people use a local distributed file system like HDFS for speed caching, right? Or maybe you're not in the cloud and you need a durable storage system, right? So where it's actually got reliability and you can be your primary storage, and then you're not going to do a cloud storage. You got to have something local, and HDFS is a pretty darn good example of one of those. So the Spark on Kubernetes system has a couple ways in which you can access, if you're using HDFS, a couple ways you can access it. One is you can have your HDFS system outside of the Kubernetes. And this was, of course, the starting place. Where I've got my Kubernetes over here, and I've got my HDFS over here, right, on a different system, maybe my legacy system, because it's got all its data loaded up on it. And I want this Spark app over here to be able to read from that guy, right? So that, of course, works. But then, why do you have to have a separate system? Why do you have to have an island over there and a continent over here? Can't you just run the HDFS on Kubernetes? And so, that was one of the work items to do. Is we've actually got an implementation where you can. It's got a description and a Helm chart that's a Kubernetes kind of package manager, where you can stand up an HDFS cluster that runs inside of your Kubernetes. I'm going to talk more about that. So in order to run your HDFS system in your Kubernetes, it uses a specific kind of pod called a daemon set. This is a Kubernetes concept. And it particularly allows you to specify all of your hosts or a subset of your host and run a data node, one per host, right? And it's designed to be appropriate for this kind of usage. I'm going to talk more in detail about this in a little bit more of a deep dive. We had to make the locality optimization work, right? So I've gotten asked the question, how performant is this? And basically, it's extremely close to bare metal. And recently, because this is going to be used in enterprise contexts, we had to add Kerberos, which is a strong encryption and authorization methodology that is commonly used with big data systems and other systems as well. And so the Spark and the HDFS can all be used with that. So I'm going to talk a little bit about the third one. I'm going to give an overview, Airflow. So Airflow is a DAG execution, it's a definition and execution engine. One of its core, and so if you're coming from the big data universe, you would probably draw analogies to Uzi. So one of the big things about Airflow is it's definitely an instantiation of the config as code. So you configure your Airflow DAGs, your jobs, using actual snippets of Python code, but the Python code is extremely declarative, right? You're not writing a lot of logic there, right? You could, but you frequently aren't. You're writing, it's got these operators, and you can declare in Python exactly what operators you want to do and how they're chained together. In Airflow, one of the key concepts is you have things called executors, right? And the executors run tasks. So your task in Airflow may be like, copy this file, or run this command, or ETL this data. And that task has to be run somewhere, and the executor is the thing that spawns the tasks. And you have this concept in Airflow called operators. And an operator allows you to specify a pre-built, more sophisticated task than just, here's a shell command. There we go. So Airflow on Kubernetes. So a couple things here, right? The core idea of the project is to allow you to run Airflow workflows in Kubernetes. One of the first things is the Kubernetes executor. right? So this means your executor that's spawning the tasks is going to run in Kubernetes, and there's some advantages of that I'm going to talk about. That's actually super important. And it also has a Kubernetes operator where you can say, hey, I've got a Docker, and I want you to run this Docker with this command, and that's your task. It turns out that there was always a Docker operator, but it had to be local to the machine that was running the executor and running that task. You couldn't offload that to somewhere else, and so Kubernetes allows you to run that Docker anywhere you want. There's a bunch of slides if you want to see more details on that. This is kind of cribbed from some of those. But one of the key things here is the Kubernetes executor, right? It allows you to get much more parallelism than you can with the off Kubernetes executor. Typically in the off Kubernetes deployments of Airflow, you have a fixed number of machines somewhere that are all your executors, right? I'm going to make 4 machines my executors, and they're going to run all my tasks. But you frequently can get much more parallelism in the Kubernetes case. And you can do things like you can define exactly what the context of your executors should be, because this is all containerized and Dockerized. So what this has allowed in Airflow is this dynamic allocation of executors. So the core way Airflow always works is you got an Airflow scheduler, and there's a bunch of tasks that are, each little blue dot here represents a task that's coming into the scheduler, and the scheduler these all represent the executors. And so it fans these tasks out to the executors, and the executors run them. And so in this case, there's 3 fixed ones. But dynamic allocation basically says, well, heck, you have a backlog of tasks to do here, right? I got my order wrong. Without dynamic allocation, let's say you only had 1 task. You have these idle executors here and here that are using resource and not doing anything. But in the dynamic allocation on Kubernetes, you basically have your scheduler. It talks to Kubernetes and says, give me some more pods to run executors. And so if it needs more, it allocates more, and when it doesn't have any work to do, it can make them disappear and run less. And so you don't have the fixed overhead of fixed number of executors, and you can get much more parallelism than you used to. And it turns out that this is actually one of the only implementations of dynamic allocation in Airflow. So it's actually a net improvement on Airflow, not just an integration with Kubernetes. So if I was doing too much of an overview before, now I'm going to do a deep dive. So I'm going to talk a little bit about how Spark is working in detail in Kubernetes. So this is the basic flow of how Spark would do an application. So you start up a Spark submit, and in this case, I'm pretending that your Spark submit is starting outside your cluster, like I'm starting it on my laptop, or I'm starting it on my server somewhere. And the Spark submit goes and talks to, this whole green area here is the Kubernetes cluster. So the Spark submit goes and talks to the API server and the scheduler and says, hey, I have some work. I have this Spark application, Mr. Kubernetes cluster that I'd like you to do. And so the Kubernetes cluster will then go take that definition, and it'll schedule the driver pod. Right? In this example, the Spark submit and the driver are separate things. And so then the driver will then talk back to the Kubernetes masters and say, well, I'm going to need some pods to do work. And just like in Airflow, Spark also calls these executor pods. They are very similar in concept, not the same ones. These are Spark executors. And so the Spark driver goes and says to the scheduler, I need some executor pods. And so then the scheduler goes and says, OK, I will schedule you some pods. And so then all of these executor pods start up. And then those executor pods go. The executor pods communicate with the driver, right? And this is one of those things that Kubernetes does for you, right? Is it allows these things to very easily discover each other. And the executors communicate with the driver, say, I'm here, give me some work to do, and the driver goes and gives the executors a bunch of work to do. And then the driver completes the job, and the Spark submit says, I'm done, and I'm happy. Or if it's a long-running job, the Spark submit might hang around for a while and say, this part of the job you asked me to do is done. Give me the next thing to do. So now I'm going to talk a little bit similarly about what we had to do to get HDFS to work. And to explain this, I have to go a little more into the way the networking works on Kubernetes, because one of the key things in HDFS is data locality. This is one of the reasons why HDFS was created to be a high performance file storage system for big data, right? One of the biggest problems you have in big data is making sure that you're not moving all of this data over the network, in a end-to-end way where every single bit is moving over the network, because that will saturate almost anything and is very low performance. So, I have a little rendering issue there. So here I've got a couple, these are the two nodes in an example here. This is, I've labeled this as basically what Spark would look like, but I'm going to tie it to why this is relevant to HDFS in a second. So I've got a couple nodes here, and there's a driver pod running in a Docker on this node, right? And then this driver will create a couple executors. Now notice, the node has an IP address, but remember I promised earlier that each pod gets its own IP address. So it can't, and the nodes run many pods, which means they can't use the node's IP address. They each have to have their own, right? So this pod has an IP address, this one has a different IP address, and this one has yet another IP address, right? All three are different, right? But they're part of the same application, and they can directly talk to each other. This pod can go ahead and talk to 10.0.0.2, and they can communicate. And Kubernetes has all kinds of fancy networking that allows that to happen at very high speed. And then here I've got a second application that has its own driver pod, and its executor pod, another executor pod, and these all have their own unique IPs, right? So this is basically what Spark looks like. Now let's talk about how you incorporate HDFS into this story. So you got these applications, right? And each node has some local storage, right? So there's some disks on each node. Now these guys aren't directly using that disk necessarily, but I've got this HDFS pods, and so I've got a name node pod, and that's not terribly important where it is. But what is really important here, and where most of the throughput is going, is through these data node pods, right? So, in these data node pods, they're running in daemon sets. I mentioned that earlier. And a daemon set has a slightly different property, that the daemon sets use the host's IP, right? So these guys have their own unique IP, but this pod, if you're going to use a daemon set pod, is using the node's IP, right? So what did that, one of the important problems to solve is various locality-related problems, and I'm seeing smiles, so people are recognizing this picture, right? This is, of course, the map from Street Fighter II, which I played a lot. And one of the key things that Street Fighter II did is they had locality, right? They didn't all, the fighters didn't all go to Las Vegas, right? They went to each other's cities, right, to go do that. Right? And so, when you saw this, you pretty much knew that it was either happening in China or Japan, right? They made themselves local. So there's a bunch of problems that you have to solve. You have to solve node locality, rack locality, and that's where which copy of the data are you accessing, and where are you going to launch the executors. So let's talk about the problems that are inherent in this, right? So the first thing, you don't want to do this. Right? You don't want to have this executor, if let's say there's a copy of the data on both data, some particular data that these both are going to read, and they're on each node, right? You don't want this executor to read this data node's copy, and you don't want this executor to read that data node's copy, right? And obviously, if there's only two nodes involved, then maybe there's a 50-50 chance of that, but scale this to 100, and if they randomly choose which copy they're going to read, they're going to most of the time pick the wrong one. So you don't want that. Right? You want this. You want this guy to pick this guy's copy, because now you're going, you're just basically going through the memory bus of your local machine, which is much faster than hopping over the network. So how did we solve this, right? So first, so let's say there's a file that wants to be read here, right? And there's a file that's going to be read here, right? And the driver tells this pod, I'd like, and let's also pretend that these files exist on both, right? File A exists on both, file B exists on both. But you want this pod to make sure it's going to read this one, and this pod's going to read this one. And so the driver's telling this guy read file A, and this guy read file B, right? And so you want, this is the communication you want that communication there. Now here's, in the problem is you want this, file A is on data node 1, which is on this IP, and that's the location of executor 1. And similarly on, and you want, that's the same thing as going to here. But the problem is that file A is on data node 1, which is on this IP, and executor 1 is actually on this IP. Now, in the yarn case, this wasn't a problem. There were no containers involved. And so the launched Spark executors were actually launched right on this host and shared this host's IP. So they could compare the data node's IP to their own IP, and they'd match. But in this case, these IPs don't match, right? And so, by default, Spark will just throw up its hands and say, well, I don't know, any place seems as good as any other, and there's no IP matches, so I don't know where to read it from, right? And so the solution was to basically add a mapping layer inside the executor, where the executor is able to tell, hey, I've got this IP, and this IP is actually located on this host, and so he does one extra layer of indirection to go from here to here, and then figure out, those match. Right? And so Kubernetes supplies an API that we can do that. We can use to do that. So the next problem is rack level locality. So the problem with, here, these are racks of computers, right? And ideally, you want to get data from, if you're on this computer, and you can get your data from your own computer, good. But if you can't get it from your own computer, you'd like to get it from another computer in the same rack and not have to transit over racks, because then you're going over an even slower networking link. Go. So now let's pretend that I have two nodes here, node A and node B, that are both on rack 1, and I have another node, node C, that's on rack 2, right? And I very much prefer, right? So here's my file A and here's my file B, and executor pod 1 is going to be asked to read file A, and I really wanted to get it from this guy and not this guy, right? Because it's much faster to read on your same racks network. And same thing for file B. Right? This is the purple is the preferred. I really don't want this, right? I really don't want that guy to read that, read from the wrong guy. So you need to know this bit, that the rack of this guy, the rack of file A, is the same rack as executor 1. The problem is the way Hadoop does this is it has lists of IPs that it says, I know these IPs are all in the same rack. And those IPs are all these IPs, the node's IPs, right? But when you look at this IP, it has no clue. Hadoop has no clue what rack this IP is in, right? And so the solution, of course, is the same solution again, map it, right? Map from this IP to this IP, and once you've done that, you can basically say, I know what rack this is in, right? 196.0.0.5, 196.0.0.6, those are both in rack 1, so I can choose to read the guy from rack 1's rack. The last thing you've got to solve is a slightly different kind of locality problem, and this is also called moving the compute to the data. Right? The other ones we're talking about reading the right replica of the data, and this is about reading, making sure that you try to put your compute in a place where the data will likely be. And so what you want to do is you want to have node preference, right? If you're going to, let's say you've got, a couple files here, right? And the driver has an idea of node affinity. And so you can say to the driver, when it talks to Kubernetes, when it talks to the scheduler, there is a way for it to express, I would much prefer you to try to launch this task on node A, and you can give it a list, right? So that it's more likely to get onto a node that has a copy of the data. Right? But there's a special API to do that. And so you might actually prefer to get these executor pods both on this node, right, until the node's full, versus putting it on this node because of network affinity. So this is an experiment we did with performance, and this is to prove that this really, really, really matters. And so it's kind of hard to read the legend here, but the blue line is how fast the disk is being read, and the orange line is how much networking is being done. So we measured the disk and the networking. And in this one, this is the kind of before we did any engineering. We did not have the data locality fix. And this application took about 25 minutes to run, right? And it was doing a bunch of disk, it's disk reading speed was being limited by how fast it could move the data over the network. And then after the data locality fix, right, most of the containers could be on the node that actually had the data, and so there's very little networking. You see the orange line has gone way down. The disk bandwidth went way up because it wasn't being limited by the networking at all. And most importantly, the duration was significantly less. All right? And this is a small cluster. This is like, I think when we did this experiment, this is like a 4-node cluster. This problem gets exponentially worse. So at a 100-node cluster, it's disastrous. This is a very important fix. The other problem that we had to solve was secure HDFS support, right? And in particular, this involves a lot of secrets. So Kerberos tickets, and then there's a thing called an HDFS token, and you also have to deal with a special case, which is long-running jobs, because these tickets and tokens expire. So Kerberos is the three-headed dog that guards part of hell, and there's a ticket and a particular concept about the Kerberos ticket, and this is important. It is for a specific machine to access a specific resource. It's not just a thing to access a resource, it's for one machine to do it, right? And so you want to translate this into tokens, which allow any machine to access this resource, because you're gonna, the resource, like a file on the HDFS, might need to be read by all these little Spark executors that are flying around the whole cluster, right? And so you want to have these tokens, and you want them to, work well for very long-running jobs, right? So this is the simplified view. I promise this is actually simpler than the real story, but you've got a user here who wants to access something, and there's this Kerberos server, and the Kerberos server is a trusted enclave, right? It actually has credentials actually stored in it, and so you have to trust that this thing is being kept secure. So the user A says, hey, I'm user A, and I want to talk to HDFS, right? And the Kerberos server goes and generates this, says, there's a secret key, and, hey, I will get this secret key to each of you, and I will promise that, if the other guy knows that secret key, you're talking to the right guy. And so the way it does this, shoot, my fonts got screwed up, and it's hard to read, but there is there's a secret key, and this is the beauty of this. This Kerberos doesn't go directly talk to the HDFS. It actually has a special copy for HDFS that is encrypted with the HDFS's password and a copy of the secret key that's encrypted with user A's password that contains that little encrypted thing for HDFS. So user A receives this, and user A, of course, can decrypt this outer envelope because he knows his own secret. But he can't crack the HDFS's one because he doesn't know the HDFS's secret, right? And then font location, I'm going to skip that. These are, this is basically multiple things being stored, a safe inside of a safe here. Go forward. This guy decrypts it, and he sends this SK1 to HDFS, encrypted with the HDFS's key, right? So this is opaque to this guy, but now HDFS has a copy of the secret key, right? And can go and now these guys both have this secret key, and they can talk to each other securely. They go back and forth many times. But this is a single host ticket, right? Kerberos generates this for this specific guy to talk to this specific guy, this user on this user's host talking to the name node. It's an admit one guy ticket. HDFS extends this concept because we're going to have a distributed system of many Spark executors that are going to talk to the HDFS. And so what happens is the first thing that a big data application will do is it'll talk to HDFS and get this thing called an HDFS delegation token, which is like a proxy that allows them to act on behalf of the driver, and HDFS will respect that. So it turns this admit one into a generic token that is for anybody who has this token. Well, now you've got these tokens hanging out, that are good for anybody. So now you're kind of worried, what if somebody gets my token? They'll be able to impersonate me on HDFS. And so one of the things you do, oh, I skipped over this. Those tokens are not long-lived. I'm going to talk about how those, they are time-bound. But you've got to share these tokens between the driver and all the executors securely, and Kubernetes provides us a facility to do this. There is a Kubernetes secret, which allows pods to communicate little bits of information to each other in a secret way, as long as they trust that Kubernetes will protect that security. So what happens is you do your Kerberos dance, right? You get a token from this ticket. The name node pod gets the token. It gets stored in this secret. And then the data node, the executors and the driver all get the secret, all get the token out of the secret, and then they can use that to talk to the data node. However, I said that these tokens don't last forever because that would be a security hole. They only last for a limited window. And so every once in a while you have to refresh this token, right? So there's not a long-lived security hole. And so there's an additional pod that we introduced here called the refresh pod, which basically every once in a while goes and talks to the Kerberos server, gets a new admit one ticket, turns that into a long-lived token, and then it updates the thing in the secret here, right? All right, let me move on. Come on, and the new version of the secret gets to all the executors. These secrets are specific per job, right? So each job has its own set of secrets here. So the secret that works for this job and the secret works for this job are not the same one. Go, go, go. They can't, like this job can't reuse this other guy's secret. So the main things that had to work here, is data locality and secrets. The one open problem, and this is getting worked on right now, is name node high availability. And so that's under design review at the moment. Let me do a quick demo. And because I did not trust that the networking was going to work right here, despite the fact that I got here and it actually did, I have, let's see, I pre-recorded this earlier today. Where is my player? And that's probably on the wrong screen, so I probably have to bring that over here. And start that about a little bit in. All right, so I'm going to explain what's going on here. Here, let me move off of that so that can go away. So this is running, this is actually running on this laptop earlier, but I've got an actual, so this, one thing I want to point out, this is on the Apache Spark, right? So this is actually, everything we're talking about here is going to be released in the upstream Apache Spark in the 2.3 branch. So it was originally developed on a fork, but it's actually going to be the mainstream code. Let's see. Go forward. Pace myself. So right now, kubectl get pods. That's the way to see what pods are running in my Kubernetes cluster. And so here wrong thing. I've got a little script here that is how I actually run. This is a Spark submit command line. It's running in cluster mode. I'm just running an example Spark Pi application. This next thing, the master, right? The key thing in this master command here is you see the little prefix where it's got K8s in the prefix. That means it's talking to a Kubernetes cluster, so that's obviously the new thing. This is the address of the Kubernetes master. You've actually got a set of IPs that you can talk to any of them. You just pick one. And then a bunch of Spark options that say, hey, here's the Spark option that I'm going to talk to. That's the master that I'm going to talk to. Kubernetes. I was going slower when I practiced this earlier. I'm going to want 2 executors. And then because Kubernetes is running Dockers, I have to say what the Docker image that I want to use is. If you are an administrator, you might configure this for your users, but in this case, I was actually being explicit about it and saying this is the Docker image that I'm going to use. And then let's go forward a little bit. Remember earlier I was talking about getting resources in. One of the resources is the jar that contains the code you're going to run. In this case, it's inside the Docker, so it's local. And this is just saying I want to run 100,000 iterations of this, so it takes a little bit of time. So we're going to run that script in a minute here, or presumably less than a minute. Yep. Let's see, let's go back a little. So I started the script in the right-hand terminal, and it's, you can see it's got, pending starting containers. And so in the left-hand terminal here, I'm going to see, hey, are there any pods running? And so now, if I look if there's pods running, we can see that a driver pod started up, right, 46 seconds ago, because I zoomed forward in the video. And then a few seconds after the driver pod started up, it did its little dance with Kubernetes and started up the executor pods. We can see the Spark UI. Go forward, go forward. So the Spark UI, the port for the Spark UI is in the running inside of the one of the pods. And so there's a way to get at its port, which is this kubectl port forward command. And for anybody who's used to looking at Spark, this looks like the Spark UI, right? So it's, for anybody who's familiar with big data things, this is going to look super familiar, right? Let me go forward. And of those 100,000 tasks that I asked it to run, it's done 16,000 or so far. If I refresh it, now it's at 25,000. So in a few seconds, but I'm going to zoom forward in the video so it'll happen even faster. It's going to be done. Let's see, click through. This is very typical Spark Web UI. We can look to see those those pods are still running. Right, they're still running. They've been running for about 3 minutes. This is running on Minikube, which is a tiny little Kubernetes instance that runs on my laptop. And I bet in a minute here, I'll go back to the Spark Web UI, and we'll see that those tasks are almost done. Yeah, so I'm refreshing the Web UI here, and you can see these tasks are almost done. And as soon as these tasks are done, right, this Spark application is finished. So I'm going to go back here, and this right-hand terminal was waiting for the application to finish, and poof, it just finished. And if we go back to the left-hand terminal and we look for the pods, they will exist no more, right? So it basically finished, right? In this trivial example here, I had only a handful of pods, but in a real system, there might be tens or hundreds of thousands of them, right? A lot more than what I'm doing here. Let's see. So quitting out of that, going back to my PowerPoint for the last little bits, if I can figure out where my mouse went. So stuff that's on the roadmap here for Spark. These are all the features that are core working. Not all of these are in the upstream 2.3, but they will be at some point. But this is all working if you look at the Apache Spark on K8s fork. Many of these are in the upstream already. Several things here that are in the kind of the yellow, GraphX, MLlib, and Spark streaming. We think these will all work, but we haven't tested them yet. So if somebody wants to try them and let us know, that'd be great. On the right-hand side are things that are not yet working. Client mode, Spark shell, because of some networking issues. They're not yet supported, but we expect to. This has been going on for over a year now. But the key milestone, basically, over last summer was there was an agreement on the Spark community. This was going to be part of core Spark. And in Spark 2.3, it's actually going to get released. So Spark 2.3 is literally any day now. It's going to be released. If anybody wants to see the detailed plan, they can see it. There's a bunch of stuff that's getting added using the custom resources. I mentioned that earlier. There's a bunch of scheduling-related preemption, things like that. that's going to be done, the ability to spread these things over multiple clouds and multiple clusters and several other ecosystem things. There's a bunch of organizations that are working on this, Google, of course, but many companies, including ourselves and Palantir and Bloomberg and Red Hat and many other companies. Here's some links to the issues if you look at the slides later that have, these are very complete issues that have design documents and things like that. You can go try it. This is the official Apache Spark branch where you can go get it. If you want to get the history or you want to get the bleeding edge, you can get that from the fork here where a lot of advanced development goes before it goes into the trunk. And I'm done. So, now that I've spoken ridiculously rapidly for very long, does anybody have questions? Yes?
Thank you for your presentation. I have two questions. First one says, you mentioned the Kubernetes ecosystem as a distro, right? Distro, since right now we have a project where it's still evaluating one distro, one speaker, right?
Mm-hmm.
You came earlier to mature distro is like a very young, like a very young phase. Do you have any suggestions? What's your opinion?
I don't have any opinion about those parts of it.
In your product, do you consider using distro?
Oh, no, so this. By the way, I should be clear. Everything I'm talking about here is not our product. This is all open source contribution. But we're not even like in our Kubernetes clusters. We're not even running either of those, right? We're because we didn't need it. That was just an example that there's many advanced features in part of an ecosystem.
Second question is, do you have any suggestions that you deploy it with Kubernetes? What's your CI/CD?
I'm sorry, I didn't understand your question. Yeah, so that was one thing I meant to ask people how they use it. So there's a lot of Kubernetes systems that are being used in development environments, and there's a few that are being used in production environments. I imagine that more will be used in production environments. Kubernetes is a common environment to use in CI/CD pipelines, right? To run things as part of a CI/CD pipeline. We use it to as part of our CI pipeline for Pepper.Data's actual main product. We test it using Kubernetes pods to do different Hadoop versions, things like that. So I definitely can say that Kubernetes is a fine and common thing to use as part of a CI pipeline. There also, in the other direction, we do have a CI pipeline for all of the big data Spark integration and HDFS integration that we used that stands up a Kubernetes cluster and runs things in it. But that's kind of not, I think, the direction you meant. The details about what part? I'm sorry.
Say you might say you have a pipeline for your big data.
Yeah. So if you let's say you had a non-trivial pipeline. That's, for example, what you might use Airflow for, right? Like if you are doing a complex pipeline of things to do, some CI or CD, CD especially pipeline, you might define that in Airflow. And of course, I talked about how you can use Airflow to say, here's all the steps that I want to do, and it'll check things for success and failure and have nice ways for you to build things out of that. So that would be a reasonable way to do it. Ours aren't complex enough that we needed that sort of thing, but that'd totally be the way that I would do it if they got complex. Yeah.
First, a simple question. So in the executor, you specify 2 executors, right?
Two what?
2 executors when
Yeah.
you run the Spark.
Are you talking about the Spark one?
It's Spark one.
Yeah.
So I was just wondering, so it actually opened 2 ports. It created 2 ports for
It created
running,
2 pods in
for
that
the
case.
executors.
3 pods if you count the driver.
Yeah, right. Counting the driver. So I was wondering, so why did it actually create 2 ports instead put 1 port and put 2 executors in that?
So this implementation always does a one-to-one mapping between executors and pods, right? So it does exactly 1 executor per pod. And it does this mainly for, I guess, we never even considered anything else. It's definitely the simplest way to do it, right? Because basically there's a single, each executor needs to be a JVM. And in this case, we didn't have to do anything complex in terms of like background processes or anything like that. Right? Basically, the Docker starts up and runs the JVM in its foreground, and when that foreground is done, the Docker exits. And part of the point here is that it costs you very little to run an extra pod, right? So it's by far the simplest way to just say, hey, each executor is going to have its own pod.
Okay. So, and I mean, so Kubernetes makes it so easy to actually auto-scale the executors, right?
Yes.
So how is that going to fit in? Because the ones which I have worked on don't have really auto-scaling for the Spark executors.
So there's a feature in Spark that I didn't get a chance to go into a lot of detail called Spark Dynamic Allocation, and that is auto-scaling for those executors, right? And basically what happens is the Spark driver, based on the amount of tasks that are outstanding and need to get done, will create more or less executors, right? And that is implemented in the fork. It's not yet in the upstream, right? But what it'll do is as it needs, if the driver has a lot of tasks that it'll do, it'll go to the Kubernetes API server and it'll say, I need more executors right now. And Kubernetes will create them pretty quick, right? Like second. And if the tasks dry up, right, there's less, like a stage completes and there's less tasks to do, then the driver will go back to the Kubernetes executor and say, I don't need those pods anymore, and they'll shut down, right? I kind of mentioned very briefly that there's also this thing called the shuffle service, right? And we had to implement an additional kind of pod that was a Spark shuffle service. In Yarn cases, the Spark shuffle service is handled by the node managers, but that doesn't exist here. The point of the shuffle service is specifically for this dynamic allocation case. Because let's say I had some stage that generated a bunch of data, and so it used a whole bunch of executors. And it generated a whole bunch of data, and then the next stage needed very few executors. Well, all these executors are all going to shut down, right? And so where's all the data that they calculated going to go before it gets to these guys? Right? That's no good. So they can't just get shut down. So they shove this data into this shuffle service, which is much lighter weight and can live for longer. So you can release the resources of the executors and just have this lighter weight shuffle service thing, right? And then this smaller set of executors can read it from the shuffle service. So that Spark Dynamic Allocation is actually all implemented and uses that shuffle service. But if you want that, as of right now, you got to go to the fork, and not the upstream 2.3.
I mean, especially, so why I asked this question is especially on the streaming case where we have a batch set, right?
Yeah.
If it actually offshoot the batch size, batch time, if Kubernetes could actually put more, executors there and reduce
It will.
the-
If
yeah,
you use this dynamic allocation, it'll do exactly that.
that'll be
Now, to be
actually.
fair, streaming was in my probably works but untested.
Right,
So
yeah.
we've tested dynamic allocation in the non-streaming case. I think that it'll probably work just fine for the streaming case, but we haven't tested it.
Yeah, I mean, I could be one of the tester for that.
That would be great. Yeah.
Do you have integration with the management UI and Spark management UI? How does it plug into
The Spark you mean the Spark Web UI? Yeah. So we do. And it turns out that the way, let me see if I can go back here. Where did my thing go? QuickTime and file, open recent. So we didn't have to do a lot of fancy stuff to get, where is it putting the screen? To get the integration with that. Let me zoom around the video and find the part that I want to show you. Okay, right here, this is the part I want to show you. So the Spark Web UI is basically listening on the driver pod in a particular port. So in order to get at that, you have to be able to point your web browser at that port. And so that port is running inside this driver pod. And so there's slicker ways to do this, but the lightest possible lightest weight way for me to do it that works well in a demo was basically to say, hey, I want to use this kubectl, port forward command. This string right here is this string right here. It's the driver pod, right? And I want to take my local 4040, and I want to point that into that pod's 4040. And so I ran this kubectl port forward, and then I was able to, the next thing that I had in this demo is I, then went to my web browser and actually looked at my local host port 4040. Right? Now you can do other things like, if you're doing this for real, you might, and you've got one particular job that you're going to be looking at all the time, you might not use a port forward. You might actually say to Kubernetes, I want to expose this port. I want you to make this port a truly public port. And then you can hit one of the real IPs of Kubernetes, and it'll give you a port number on its real IPs, and then you can look into it that way, right? But we didn't actually have to change anything in Kubernetes. Kubernetes supplies a few different mechanisms to expose the port, and then you can get at this. Yeah. Could be. Well, you could certainly, if you look at Yarn that's in Hadoop 3.0, right? One of the things that Yarn 3.0 calls a marquee feature is the ability to run long-running applications, right? And it has Docker containers, although the Docker container, I think, got delayed to 3.1, but it's coming soon. Oh, 3.2? OK. Anyway, but it's coming soon. You're absolutely right? If you squint, and you don't have to squint very hard, right? Yeah, Kubernetes and Yarn, kind of, maybe they're two sides of the same coin, right? Now, Kubernetes provides a bunch of functionality that Yarn does not, right? So this advanced networking layers, right? Yarn does not have that sort of thing, and it would be a little harder for Yarn to do that sort of thing because Yarn is not so opinionated about containers, right? You don't have to have a container to run something in Yarn. You have to have a container to run something in Kubernetes, right? So they've got a little different requirement. My personal belief, and this is my prediction of the future, so I'll look back at this video 10 years ago and see whether I was ridiculously wet or not, is that Yarn will not jump from the big data island to the continent, right? But it'll remain a serious force when you have a big data island. But Kubernetes will enable the big data work to be done on the main continent, and it will be a major force of the way to do it. So I don't think Yarn's going to die, but I do think that many of the big data, especially when they're not necessarily a dedicated system, will be able to be done on Kubernetes, right? And I think that even though Yarn and Kubernetes could kind of do each other's job, I don't think they'll actually end up being used in a completely interchangeable way. I think Yarn will stay focused on the big data. That is my opinion. All right. Thank you very much. Thank you for those good questions.
Best show today.
Best show? Yeah, thank you. Wonderful.
Great talk. Thank you for coming. Please clap after yourself. Next month, we're going to have Brent Chapman there at the back speak about incident management in regards to IP. So you should come back for that. And thank you for coming.
What's going on with my mouse?